Hello and welcome everyone. My name is Amanda Sturkenberg and I'm the Content Marketing Manager here at REGENESIS in Europe. Before we get started, I just have a couple of admin items to cover. We're trying to keep this webinar within the hour. Now, if you start experiencing some quality issues with the webinar itself or just the quality of the audio, please try refreshing your browser first. If that doesn't help, please disconnect and repeat the original login steps to rejoin the webinar. If you have a question during or after the presentation, we really encourage you to ask them, and you can do that using the chat feature located on the webinar panel. Now, I'll collect all the questions and we'll do our best to answer them at the end of the presentation in a separate question and answer session, Q&A session. If we don't answer your question within the time permitting, we'll follow up with you after the webinar via email. Just to let you know, we'll also be recording this webinar and a link to the recording will be emailed to you once it is available, which in this case might be a bit longer than normal, probably within the next couple of weeks. So in order to continue to sponsor events like this one, then we'll be sending out a brief survey following the webinar to get your feedback. In today's presentation, we'll discuss PFAS, lessons learned from treating a large-scale AFFF site using in situ colloidal activated carbon. And with that, I'd like to introduce our presenters for today, Rebecca Mora, Associate Vice President and Senior Technical Leader at AECOM in the US. Now, Rebecca Mora has over 25 years of environmental investigation and remediation experience. She specializes in the design and implementation of innovative technologies, particularly for groundwater sites contaminated with current or former emerging contaminants such as PFAS, 1,4-dioxane, perchlorate, and hexavalent chromium. Most of her career has focused on in situ remediation with an emphasis on developing solutions for industrial and federal clients' environmental challenges in the US. And she will be joined by Ryan Moore. Ryan is our PFAS Remediation Program Director here at REGENESIS, and he has over 20 years of experience as an environmental project manager and also as a laboratory account executive relating to multimedia contamination sites throughout the US. His key experience is in situ groundwater and soil treatment, but also site investigations, corrective action evaluations, operation and maintenance of remediation systems, large soil removal remediation projects, vapor intrusion assessments, and environmental laboratory operations such as QA/QC evaluations, data interpretation, and business development. All right, well, this concludes our introduction, so I will now hand things over to Rebecca to get us started.
Thanks for that introduction, and thank you all for joining today. I'm looking forward to sharing the results and lessons learned from an interesting site we've been working on for more than 2 years now, where we're treating PFAS in groundwater at a former fire training area. And based on recent discussions with REGENESIS, I believe this project is still the largest full-scale PFAS treatment with colloidal activated carbon to date in the world. So that may provide some perspective as we go through the presentation. So this is a brief overview of what I'll talk about today. I'll just have one slide on what is plume stop, just in case there's anyone out there that isn't familiar with it. I'll go over some site background that's relevant to the rest of the slides. I'll go over a pilot study very briefly that supported our injection design. Then I'll spend most of the time on the full scale. We'll talk about the installation of the barrier. We'll talk about results of 2 years of monitoring, and then I'll summarize all of the lessons we learned during this project to share with all of you. So what is plume stop? Well, it's colloidal activated carbon, so very small particle sizes, about 1 to 2 microns, and it's suspended as a colloid in polymer solution. So that helps it be distributed in the subsurface. And essentially, plume stop coats the subsurface soils and turns them into a purifying filter. The carbon in the subsurface absorbs contaminants, and you can inject this product perpendicular to groundwater flow as a treatment barrier, which is what we used at this site. So here is an aerial view of the site. It is a former fire training area. Over on the left-hand side, you see those green rectangles. Those are the former source areas. The black dashed line around the property is the property boundary. And then you can see just outside of that property boundary are a couple of ditches. This solid blue line is a ditch that always has water in it, and that is because there is groundwater venting to that ditch. Over on the left-hand side is another ditch that is dashed that only seasonally has water in it. So we have about constant groundwater flow over on this part of the site that is towards the ditch. Over in this area, we have variable groundwater flow depending on the season. And when we first arrived on this site, there were only about 5 wells here. And so we chose the highest concentration well to perform our pilot study at, and that is over here just down gradient of one of the source areas. So this is the approach we used for the pilot study. We had 5 injection points represented as those red dots. We had 6 temporary piezometers that are the blue triangles, and those were used to evaluate plume stop distribution during injections, both down gradient and cross gradient. We also had 2 performance monitoring wells located 7 and 9 feet down gradient of the injection points. And after injection, we collected 7 post-injection soil cores to confirm distribution. So that gray shading around the wells and cores and piezometers, that represents the extent of plume stop distribution. And below is a photo of an example conformation core, which shows plume stop distribution within the more permeable soils here in this black area and as well as down here. So what did we see in the pilot study? Well, we saw very rapid decreases in concentration. We had more than 99% reduction of PFAS, PFOA, and PFHXS. There was significant reduction in concentrations in both wells by the first monitoring event, which was about 1 month after injections. We had a little more gradual reduction of PFOS in well PZ1, and that's because it was further down gradient. If you look at the total PFAS in MW11, you do see that there's a little bit of increase after injection, and that was due to some rebound of short chain PFAS compounds. So after the first sampling event, which was performed in the end of March, we received the data probably about the end of April. And as soon as the client saw that, they said, we're sold, we want you to move forward with full scale, and we want it installed in June of 2021, which was 2 months away. So let's talk about that for a second, because normally when I work on remediation sites, I like to have a fully developed conceptual site model, understand the site better, and that just wasn't going to happen at this site. The client was interested in moving rapidly to full scale. There was perceived regulatory as well as public pressure. They wanted to show action, that they were being proactive. And so what we agreed on as an objective is to reduce PFAS concentrations in groundwater, migrating towards the nearby offsite ditches. So we did not have numerical criteria for this installation. Okay, so let's talk about the site characterization we were able to do. So actually, while we continued monitoring the pilot test, we went out and installed a bunch more wells around the boundary of the site. So we installed about 14 new wells, and we collected samples and analyzed them for PFAS compounds, as well as potential co-contaminants that could also be competing for plume stop absorption sites. So what we found was only one significant co-contaminant, which was DRO, or diesel range organics. And this map shows kind of the range of concentrations that we detected. So we'll start with PFAS first. Those are the red, orange, and green colors. You can see that red is the highest concentrations. This well over here on the left-hand side was the highest concentration at the site, total PFAS of about 550,000 parts per trillion. The orange wells, which are primarily over here on the left-hand side, near the former source areas, those ranged from 20,000 to 100,000 parts per trillion total PFAS. And then when you get further away from the source areas, you get down into the green color, which is about 1,000 to 20,000 parts per trillion total PFAS. The DRO concentrations are represented by single yellow circles or double. The single circles indicate DRO concentrations between 1,000 and 5,000 parts per billion. And then the double circles here represent 5,000 to 10,000 parts per billion. So DRO was primarily detected over in this portion of the site, as well as this high concentration PFAS well over here. And one thing that's really important and interesting, I think, is this well with the highest DRO concentrations had the lowest total PFAS concentrations, a good order of magnitude lower than its neighboring wells. So that will come back up when we look at the results. This is a cross-section of the site, and there's so much I could talk about on this slide, but in the interest of time, I'm going to limit it to what's important to share with you all for context when we discuss the injection activities and results. So the first thing that's important to point out is that it's a perched water table at this site. So depth to water is generally about 2 to 4 feet below ground surface, but deeper as you get towards the right-hand side of the cross-section because of that hill. The top few feet is reworked urban fill with high permeability. Below that, we've got sand and sand silt mixtures, and then followed by a thick continuous clay layer that starts at about 6 to 8 feet below ground surface. So these are really favorable site conditions for plume stop. You know, you've got permeable sediments for good distribution of plume stop. It's not deep, and so you save on drilling costs. And then you have that nice confining layer with the clay to tie your barrier into. On the northern end of the site, which is the right-hand side of the figure, you can see depth to water gets deeper and also depth to clay gets deeper. So we're dealing with a thicker saturated zone over there. Also note the 6-foot thick gravel deposit over on this side of the cross section. That will come into discussion later when we're looking at results. Also, something important to look at is over here, there is a highly transmissive shallow zone in the vadose zone in this area that extends from this MW08 over to about MW11. So that's down to about over here, this part of the barrier. This is a very highly transmissive zone, and we'll talk more about that when we get to the injection activities. So we performed slug tests in each of these new wells to provide estimates of hydraulic conductivity. And then with that information, as well as the lithology and the concentrations, we put together the full-scale design. Okay, so this slide kind of shows the design of the barrier, and I'll walk you through it because there's a lot to talk about here. The first thing we'll look at is the barrier geometry. So you may notice that the barrier is a decent distance away from the site boundary. And that's because we don't know exactly how long this barrier is going to last and how long it will be needed. So we wanted to leave room for a future second barrier should it be needed in the future. You can see how it's nice and straight along the left-hand side of the figure, and then you turn the corner and it's definitely not straight. We had a lot of subsurface obstructions that we ran into. We did actually perform geophysics along this whole area before injection, but ground penetrating radar does have some limitations, so we still had several unexpected subsurface obstructions that we were able to work around because we were using an injectable technology. So moving on to the color coding. Over here in the legend, you can see what the colors represent. So you've got green is 100% plume stop concentration, yellow is 150, and red is 200. So the 100% is essentially the calculated plume stop demand. And then the yellow and red represent safety factors that were applied to that calculated plume stop demand. And that was either due to the presence of DRO at that location or really high PFAS concentrations. These safety factors were also applied because we were trying to manage the risk of having a less detailed conceptual site model. The different dashes along the barrier represent deep injections. So sections E, F, and G are where we had the deep injections. And then over in section A, we actually performed intentional mounding over there. And that's because in section A, the water table can be very shallow, 6 inches to near surface sometimes of the year, but we can't directly inject that shallow. So what we did is created some mounding during injection, which resulted in some distribution above the injection interval. So in the middle there, we've got kind of what I call our injection statistics. It took us about 3 months to install this barrier. It's about 1,635 feet long, required 660 injection points. We injected primarily from 3 to 7 feet below ground surface, except for the deep injections, which were 6.5 to 14.5 feet below ground surface. And then all in all, we injected about 295,000 pounds of plume stop. Okay, this slide talks about the injection approach as well as it has some photos from the injection. You can see over on the left-hand side there, we had injection points every 5 feet, and they were in 2 staggered rows. We did have 2 injection rigs out there, each of them injecting into multiple injection points at once, trying to be as efficient as possible with the timing. We had piezometers and confirmation cores every 50 feet to evaluate distribution. That's called design verification. We installed the piezometers ahead of injection, and then we also used that lithology data to update the injection design as necessary. Because if you recall, we had just 14 monitoring wells around the perimeter, and they were 100 to 200 feet apart. So it was really helpful to collect some additional information in between those monitoring wells while we were out there. And because we were gathering this additional lithology data and also encountering subsurface obstructions while they were injecting, we used Microsoft Teams chat, where we had the field crew from AECOM and REGENESIS, and then the office staff from AECOM and REGENESIS, all on the same chat. And the field folks were able to tell us what they were seeing. We were able to have input, make decisions real time, and keep things moving. So it really ended up being kind of a best practice. We did experience some surfacing during the injections, especially in the shallow water table areas, but we essentially contained those and let the plume stop infiltrate back into the ground over time. So at this site, that wasn't a particularly big deal. We also had one instance of plume stop daylighting in the ditch. And this was due to that shallow, highly transmissive zone I pointed out previously on the cross section that's right below ground surface. And what happened is when we injected, there was some mounding and it raised the water table to intersect that highly transmissive vadose zone, and plume stop traveled along that transmissive zone to the ditch. So for the rest of the injections along that highly transmissive zone area, we used what is referred to as a parking agent. So the parking agent was either liquid calcium chloride, or in some cases we used gypsum as a solid, which is calcium sulfate, and the calcium component destabilizes the colloids in plume stop and flocculates the carbon so that it is no longer mobile. So while we were still injecting in that troublesome area, we used the parking agent, injected it down gradient, or emplaced it down gradient of where we were injecting, and that limited the migration of plume stop beyond that point. So this approach resulted in no more daylighting during the rest of the injection effort. Okay, before we get into results, I wanted to talk about our monitoring approach. So we designed this monitoring program to have 2 types of wells: in-barrier wells, which are shown in blue, and down gradient wells that are shown in purple. So the in-barrier wells, we used those to evaluate the health of the barrier itself. And then the down gradient wells, we wanted to be able to evaluate improvement of down gradient water quality over time. So the way it worked is if plume stop was detected in an existing well during injection, or even slightly after injection, it became an in-barrier well. And then we installed a down gradient well outside of the plume stop distribution in that area. If plume stop was not detected in an existing well after injection, that became the down gradient well. And then we installed another well up gradient of that well within the barrier. So you'll notice over on the left-hand side of the figure that some of the down gradient wells are further away from the barrier. So over on this side, the purple wells are pretty far away from the barrier compared to some of these over here. And that's because we have a above ground utility over here that we can only get so close to. And so this comes into play when we look at results and where we might expect down gradient effects already or not. All right, now we'll transition to results. And I'm going to show results from 5 locations around the barrier that I think are interesting or might illustrate a point. So each slide will have graphs of the in-barrier well and then a corresponding down gradient well for that location. So this well pair is located very close to the source area. You can see in the top right here, I've circled where it's located. So if you look at the in-barrier well, there is a 99% reduction in PFAS and PFOA concentration, but not until after May 2022. And this is after we replaced this monitoring well. So why did we do this? Well, as I mentioned, there were some historic wells on site when we first took on this project, and MW05 was one of them. So when we saw that the results were not what we were expecting in the in-barrier well, because we did see plume stop distributed to this well, not as much as we saw distributed to other wells, but it did arrive. So we made it an in-barrier well. We didn't see the performance that we were expecting. So we looked back at the borehole log for this well, as well as we looked into many other things too. And we noted that this well was not screened across the primary transmissive zone. So we replaced this well with PZA1, which is located just a few feet away, and we collected a core ahead of time to ensure that we were intersecting the main transmissive zone and that there was also evidence of plume stop in that area. And then we installed the well, started monitoring it, and you could see that we had much better results, more representative of an in-barrier well. Had about 99% reduction and holding pretty steady. If you look at the down gradient well, it's located quite a distance away, about 53 feet down gradient from the barrier. And the groundwater velocity at this site is only about 10 feet per year. So we weren't really expecting to see much impact in this well from treatment yet, but we're certainly continuing to monitor it. And one thing we did notice that I'm sure is jumping out at all of you is we had a very significant spike in concentration, followed by going back down. And the reason for this is because this well is close to the source area, and there is likely source material present down gradient of the barrier. And these temporary spikes can happen during wet periods, as this area is prone to flooding. So we'll talk more about infiltration in the next few slides. Okay, moving around the barrier, now we're up here. And this, as you may recall, is the highest PFAS concentrations at the site. And I'm just personally really impressed with the graph on the left. I mean, that is almost 100% reduction in concentrations and holding steady for at least 2 years so far. So very pleased with those results. Again, the down gradient well to the right is located 54 feet down gradient. So again, we're not expecting to see much effective treatment at this point, but certainly we see some interesting behavior in that well. And these spikes in concentration are likely due to infiltration and leaching of PFAS mass from the vadosome. And we'll show you some other lines of evidence for that theory in a minute. But the concentrations do decline after each peak, suggesting that the base flow is really at that lower concentrations. And it's going to take some time to see downgradient effects of treatment at this location, but the barrier itself is really holding strong and mitigating further migration of very high concentration groundwater towards the ditch. So we took a look at these PFAS concentration fluctuations and graphed them against temperature to see if there was correlation. And as you can see, there's a very strong correlation with temperature. We have a 34-degree swing in temperature where the increases correspond to increases in PFAS concentration. So what that indicates is that warmer water during the wet summer months is infiltrating from ponded areas at the surface through the vadosome down to groundwater. And so this becomes an additional line of evidence supporting that what we're seeing with these swings is leaching of PFAS mass to groundwater due to infiltration. Similarly, we looked to see if there was a correlation with conductivity. And as you can see, there was also a good correlation. So the high conductivity corresponds with the high PFAS concentrations, and the values we're seeing for conductivity indicate an anthropogenic source. So that makes sense that it was in the fire training area. So if these PFAS spikes were due to just regular groundwater advection, we would not see these kinds of swings in geochemistry. So these graphs show how you can look at other water quality parameters to help you make sense of the concentration variability in your results. Okay, moving along to this part of the barrier here. And again, this is where we had the high DRO concentrations and the low PFAS concentrations. I just want to point out over on the y-axis here, I mean, look at these numbers. They're just so much lower than what we're seeing in the other wells. So what we saw here was a very slow decline in PFAS concentrations, about 34% over 2 years in the in-barrier well. And this is likely due to competitive sorption from DRO. And that's supported by the fact that DRO has been reduced about 97% at this location. So we have limited reduction in PFAS in that in-barrier well, but also concentrations are very low. So it's not a lot of risk to our receptor. If you look at the down gradient well, it looks like there's a lot of fluctuation there, but really, if you look at it closely, the PFAS concentrations are fluctuating between 150 and 450 parts per trillion. So not really that significant. And we're not expecting to see, real impacts down gradient until we see more treatment in the in-barrier well at this location. So this area highlights the potential impact of co-contaminants on plume stop applications. And fortunately for us, the PFAS concentrations at this area were 3 orders of magnitude lower than other parts of the barrier. So it's not a real concern for us. Okay, we're going to wrap up with 2 more areas of the barrier that actually are showing improvement already in down gradient water quality. And this is because of 2 reasons. First, these wells are away from the source area. And 2, the down gradient wells are closer to the barrier. So if you look at the in-barrier well here, we show about 99% reduction. We do see a recent uptick at the 2-year mark. So we'll continue monitoring to see if that's just transient or if the trend continues. But it's important to note that all of the PFAS compounds showed the same concurrent slight uptick, which means that it's likely not breakthrough. If it were breakthrough, we would see short chain PFAS breakthrough first. In the down gradient well, we see about 80% reduction to date and holding steady there. This indicates that the barrier is effectively reducing groundwater concentrations down gradient, migrating towards the ditch. Okay, now we're going to talk about our last well pair, which is up here in the top right corner at the end of the barrier. And this area of the barrier is also showing improved down gradient water quality, but after some optimization efforts. As you can see, there was a quick rebound after the initial injection for the in-barrier well, and no real significant decreases in the down gradient well for about the first year. So if you recall, this was the area with the longer, deeper injection interval, and also that 6-foot thick gravel deposit. So that's important to consider because the initial injections were what's called bottom up, which means you push the direct push rod to depth, and then you expose the injection screen, and then inject the plume stop as you pull up the rod. And based on what we were seeing, we thought maybe the plume stop may have followed a down and out preferential pathway near the bottom of that target interval where that gravel deposit was. So what we did is we performed some supplemental injections in this same area, but we used a top-down approach to ensure that the distribution into the shallower portion of the injection interval. So cores were collected to confirm distribution in the shallower interval, and then after the injections, we had 99% reduction observed in both the in-barrier well and about 96% reduction in the down gradient well. So we'll wrap up the results with a summary. So based on 2 years of monitoring data, the barrier appears to be holding with no evidence of breakthrough, even in those really high PFAS concentration areas. The in-barrier wells respond more immediately, and the down gradient wells response depends on distance from the barrier and also whether there's residual PFAS mass already down gradient of the barrier. Down gradient wells located in areas away from the historical source area are performing best. DRO can compete with PFAS for sorption to plume stop. And then finally, we're going to continue monitoring to further evaluate longevity of the barrier, improvement in down gradient water quality, and the need for any further injections. So this is my last and favorite slide, frankly, that summarizes the lessons we learned during this project. And again, when you install a barrier this large and it takes 3 months to inject it, you learn a lot of lessons. So what we learned is daylighting of plume stop can be effectively managed using calcium-based parking agents. We learned that co-contaminants compete with PFAS for sorption sites, particularly if those co-contaminant concentrations are high. So if you have a site with high co-contaminant demand and it's affecting your ability to meet your treatment objective, you may need to have supplemental injections. If early results are not as expected, we recommend revisiting lithology and also your plume stop distribution. This might involve collection of additional cores in the areas where you're not seeing good results. And it might show that you may need supplemental injections if you have gaps in your distribution, or installation of new monitoring wells if they're not screened appropriately. We learned that you can look at geochemical data to help understand trends in PFAS monitoring data. The plume stop barrier is performing best away from the source areas, which is really a more typical location for plume stop to be applied, is kind of at the toe of a plume. However, we did see that increased concentrations of plume stop have been effective at addressing really high PFAS concentrations for at least 2 years. So is something that we learned is that this could be applicable to source area control objectives. And then finally, the biggest thing we learned is that while it was challenging, we were able to design and implement a rapid, full-scale plume stop barrier installation that was successful at significantly reducing PFAS migration towards a receptor. All right, thank you everybody for your time, and Ryan, we'll pass it over to you.
All right, well, thank you, Rebecca. That's a great presentation. My name is Ryan Moore. I'm the Program Director for PFAS Remediation here at REGENESIS. It's a newer role for me. I previously have been the last 11 years with REGENESIS as the Great Lakes District Manager. Now I'm taking over this exciting role as the Director of PFAS Remediation. Real quickly on the presentation this afternoon, just going to get into kind of a typical PFAS site conceptual model that we review when these projects come in, a little bit about plume stop and source stop. So I'm going to talk a little bit about some common treatment approaches and then a couple of project examples in addition to what Rebecca presented earlier. So full spectrum treatment for PFAS. What does that mean? When we get project data packets, oftentimes we're trying to look at, the PFAS contamination in multiple areas within a project site. On this graphic here, we have this labeled as A through D. A being that vadose unsaturated soil, typically the source mass that needs to be addressed if you're wanting to look at a long-term remediation effort for PFAS. B is that capillary and fringe area. This is really important because oftentimes many of these PFAS compounds want to hang out at that air-water interface. So if we've got a treatment approach that you can attack that, you can significantly reduce mass discharge into the groundwater. Obviously, when looking at source groundwater concentrations, having that tool to be able to address that is beneficial. And then most often when we're utilizing just plume stop or just a groundwater treatment approach, we're looking more of that distal end of the plume for lower concentrations. So just kind of think about these different areas as we walk through this. I'm not going to get into very much about what plume stop is. Rebecca did a great job in explaining the technology. I do just want to mention that, we have source stop as well, which is another formulation of our colloidal activated carbon. As the name suggests, it is formulated for those source area projects. For the soil treatment, what are we typically trying to do and how are we utilizing the colloidal activated carbon? In this case, we're going to use source stop. Again, if you're looking at the unsaturated soils, oftentimes we will employ a stabilization or mechanical mixing of the soils with the source stop. This has a couple of benefits. The main one is we're trying to reduce that leachability of PFAS from the soil to the groundwater, right? We're trying to be protective of the groundwater or prevent additional mass discharging to that groundwater. The same thing is with this kind of excavation application or horizontal barrier. Again, we want to kind of coat the bottom of the excavation, allow that source stop to kind of permeate in that capillary fringe to attack zones that we know there'll be high mass residing. An example of what we're doing from the source treatment, in 2022, we did a kind of a pilot test or a proof of concept test at the Grayling Army Airfield, where we had one building where they used to park fire trucks outside of it, and the fire trucks leaked with the foam. And so instead of fixing them, they would just continue to add foam to it, and it created these kind of like mini source areas. We just wanted to, again, do a demonstration of the effectiveness of the source treatment. And so we picked a small area around this building where we knew we had high impact and did a stabilization treatment effort. So what did that look like? Again, this is kind of a combination of the horizontal barrier and the stabilization. We just picked a small area, kind of a test cell that we used, where you can see the source stop going in. It's a black coloration liquid. We apply it in the bottom of the excavation, kind of spread it around. And then we would backfill and mix the overburden soils with the source stop as well. Again, the goal is to reduce the leachability of that PFAS from those soils. Looking at what the summary of the scope, this is really small. Again, 225 square feet, 0 to 10 feet. Groundwater is typically around 14 to 15 feet in this area, I believe. We're really just looking at preventing leachability of the soil. When you're completed, this is ideally what it's going to look like. You spread everything back out, get it compacted in, and then restore the site surface. So when you're done, it would just be clean grass here. So what does that data look like now? Well, we collected the baseline sample. These are soil samples that were ran through the SPLP leach analysis. And you can see from right after we completed the mix, we collected that sample and we sent it to the lab. We had a 99.4% total PFAS reduction of the leachate. We then went back out to the project site about 6 months later and collected some additional soil cores and wanted to see how is it holding up. And as you can see, at 6 months, all the results were non-detect in that leachate. So it demonstrates the power of coming in and treating site soil. So now no longer have that PFAS leaching into the groundwater. So what are our groundwater approaches? Again, going back to the full spectrum graphic that I showed a minute ago, we're looking at both the source and plume areas. The source, we can inject the source stop right below where you may do soil treatment or soil removal or soil stabilization, whatever it may be. Come in and do the injection. Again, we're trying to attack the areas with the high PFAS levels, and we're trying to help with any type of treatment down gradient or to help attenuate that PFAS plume with other efforts down gradient. On the more traditional groundwater plume treatment, oftentimes this is a PRB or permeable reactive barrier. These PRBs can be installed through traditional direct push injection, just like the site Rebecca was showing you, and that's how that project was completed. But you can also come in and, if it makes sense, and do more of a soil trench application. We're doing a project right now, actually, as we speak, where they're going in and doing a 600-foot long plus trench along a construction area, where we're blending in the source stop into an aggregate so that as site groundwater migrates through from the construction site, it's being treated through that source stop trench. You can do the same thing with a traditional plume if it's shallow enough where it makes sense, but oftentimes it's more of the direct push in traditional injection scenarios. The example project I want to show is this is a New York brownfield site where the client came to us a few years ago. The project itself was a former bulk storage refinery area, so very similar setup where Rebecca was just talking about. In our case, however, where we were treating, there were no co-contaminants. The site was only concerned with PFAS and PFOA. The objectives of the site was to do some source stabilization that the client did on their own, and then utilize the plume stop as a PRB. This soil stabilization area is highlighted here in this kind of red oval, and this was directly up gradient of where we did the plume stop barrier along the property boundary here on the bottom right. The geology of the project site was mostly silts and clays, but they did have some high permeable sandy zones where that groundwater and that PFAS migrated through. So what did it look like in reality? So we go out, this MW12 was the original monitoring well that was kind of used as our baseline and for our design criteria. And then MW16 was the monitoring well that was installed later as the down gradient monitoring point of how well is this working. Before we actually did the application in MW12, we did deploy our flux tracer mapping tool. Our flux tracers are units, I know we've had previous webinars on these, but if you haven't seen these, they're really cool. But in essence, they're units that go down into the monitoring well and help us really identify flux zones within that monitoring well screen. And so that's what we did here. We wanted to really confirm the groundwater velocity and make sure that we didn't underestimate the speed of groundwater or underestimate the contaminant mass flux. If you did, you may have to do some modifications in the design. The application here was a permeable zone between 13 and 17 feet. And in this case, we actually applied about 12,000 gallons of the plume stop in a 3-row configuration. So we wanted good overlap and kind of a nice thick treatment zone perpendicular to groundwater flow. You can see too that the concentrations were not nearly as high as they were at Rebecca's site, but about 2,000 part per trillion total PFAS. Again, PFAS and PFOA are the primary constituents of concern. So what did the data look like after the application? Here's the baseline. This is the down gradient monitoring well. See where the application occurred. They did some sampling about 10 months and 17 months post-application. We've maintained a greater than 96% reduction in that monitoring well, about 15 feet down gradient. Unfortunately, there's no in-barrier monitoring wells to kind of show like what the barrier itself is doing, but this was great news and kind of a great data set that we expected, and then it's been maintaining over time. So I think when they get more data in, we'll be able to update these graphs accordingly. More importantly, at this project site, again, being part of the New York Brownfields program, they had to get this remediation completed as part of the development so they can be issued their certificate of completion through the New York Brownfields program. This is a really important step for developers in New York, where oftentimes it's kind of a betterment approach. They need to go out and do the best that they can, or the most good when they're going out for the development to achieve ultimate risk reduction of these contaminants, which is what happened here. So as I close, I just want to kind of talk about some common scenarios. We've kind of went over a couple of project sites that we're seeing treatment from both the source and groundwater. We're doing a lot of projects right now that are kind of formed around construction activities. Oftentimes these are airports, right? Where airport, it may be building new hangars, or they're going to be doing runway reconfigurations. At that time, it's great to get the treatment of those site soils done then, right? What's the benefit? Well, one, what they've done in the past when they had these PFAS impacted soils is they're just stockpiling it. They're building kind of a temporary holding cell. They'll stockpile it, they'll cover it with plastic, and it just sits there, and they don't really know what to do with it. So if you could do the treatment during the activities, then you can get to more of a reuse scenario very quickly versus stockpiling and holding on to that. The other alternative, what they're often doing as well, is they may just trying to go for disposal. They're going to send this, they're going to excavate the soils, they're going to take it to a landfill, and really they're just transferring their risk or their liability from on-site to off-site, and then they have risk along the way of that transport. So a better way to do it would to just go ahead and treat while you're there. We do this a couple of ways. I just talked about the excavation application. You could do blending the site soils and reuse on-site or different areas, or spreading out. Anything you can do to not take the soil off-site. At the end of the day, ultimately, again, why are you doing it? We want to be more protective of the groundwater in these areas. Real estate transactions. My second example was the New York Brownfields program, right? Redevelopment. A lot of times, a lot of these sites we're looking at is, hey, I've got this brownfield project. I would really like to, do something for PFAS. Maybe the regulations really aren't there for them in that area, but they want to do good at the project site. So they see it at that as an opportunity to do treatment because of the transaction or because of the development. The other ones we're seeing a lot of is where, a company is selling an existing facility and they know they got PFAS impacts. And so it speeds up the need for remediation prior to that transaction closing. Again, what are they doing? Both the source treatment of soils and then groundwater treatment. And then finally, the most common scenario I think we get are existing properties, very similar to what Rebecca presented on you. You've got a project that may have a contributing source to a larger plume. They've got to be protective from receptors because they have regulatory agencies asking questions or requiring them to investigate. And they're looking at ways to be proactive and try to do treatment now, while they have a little more control of the process. Additionally, one thing I really haven't talked about, we're not going to get into too much, is that, in all these cases, we do have a 10-year warranty through our Plume Shield program to offer warranties for long-term groundwater treatment at project sites. My final slide here, and then we'll open it up for questions. I just wanted to kind of highlight, again, the diversity of the types of projects that we're working on. Yes, airports are a big component. You see that on the left, but this is just an example set of our sites. This is by far not the full list. We've got over 50 projects worldwide now, so you can't get them all on this slide, which is good. We're doing a lot of good there. But again, airports are a big component. Department of Defense facilities, the Grayling facility is one. We've done several different confidential Air Force and Navy facilities. We're doing research through different DoD programs as well. So we're constantly learning and doing more with the DoD. Commercial manufacturing is another big component of the project sites we're looking at. And this could be anything from former paper mills to chrome facilities, any manufacturing facility that probably either utilize PFAS in their processes or utilize raw materials that had PFAS on it that maybe they didn't know or did know that it was there, but they've had a release in some place. And then finally, landfills and bulk fuel storage and refineries. Again, this is the exact same example of what Rebecca had. We're seeing a lot of those. And why are we seeing this? Because all these facilities had fighting foams there because it's the best approach when putting out fires of those natures. So, most often if you start looking for PFAS, they're going to be there and you'll need to address them at some point. With that, I appreciate your guys' time. Thank you again, Rebecca, for such a great presentation, and we'll open it up for questions.
Great, thank you very much, Ryan. Well, this concludes the main presentation, so now we're going to shift into the question and answer session. But before we do this, just a quick reminder that you'll receive a follow-up email with a brief survey. We really appreciate your feedback, so please take a minute to let us know how we did. Also, attached to this email will be your attendance certificate, so do keep a lookout for this email. It will be sent automatically from the goto.com domain, so keep a lookout and also check your spam folders if you need your attendance certificate. Right, so let's take a look at the questions here. The first question is regarding other alternative remedial approaches. Were there other remedial alternatives considered prior to implementing the plume stop at this site? If so, what were the alternatives and the costs?
Okay, well, there was a previous alternative developed by others that was a pump and treat remedy. It also included a slurry wall and capping of the fire training area. And that estimated cost was, I believe, around 20 million. We brought some passive treatment options to the client. So we evaluated, I think it was about 3 different alternatives. One was an injectable PRB, like the colloidal activated carbon one I talked about today. The second was a continuous PRB, where you use continuous trenching and backfill with a treatment media. And then the third was a funnel and gate, where you install, low permeability walls to direct groundwater towards permeable treatment zones or gates. So we went with the injectable PRB, as you all know, and that was because we knew that based on the history of the site, we were likely going to run into subsurface obstructions, and we really needed that flexibility of an injectable PRB during installation.
Okay, thank you, Rebecca. Right, let's go to the next question. What is your monitoring frequency?
Sure. So we collected samples monthly for the first 3 months. Then we switched to quarterly. And then after reviewing the 2-year post-injection results, we actually recommended switching some of the wells to semi-annual as a cost savings measure for our client. And these were wells where we are seeing a well-established trend after 2 years.
Okay, thank you. Let's take a look. Here's another question. Did you see any evidence of the carbon migrating to the downgradient wells?
No, we did not. So for 2 years now, our downgradient wells have remained unimpacted with plume stop, and that's based on, essentially the groundwater has remained clear in these wells. It's pretty obvious when the plume stop arrives at a well, it definitely turns black or grayish, and we have not seen that in our downgradient wells.
Okay, yeah, great. Thank you, Rebecca. This will probably be our final question. Have stakeholders been pleased with the performance to date?
Yes, they have. They've been very pleased, actually. Both the client as well as two different regulatory agencies have considered this a success. Fortunately, they do understand the limitations of already having some PFAS mass down gradient of the barrier in certain areas, but they're generally very pleased with how the barrier is holding up and with the down gradient water quality improvements that we've observed to date.
Okay, thank you very much, Rebecca. So this is now the end of our questions. I can see some others have come in. I'm sorry if we didn't get to yours, or if you think of some more questions as you go about the rest of your day, you can always email us, and any of the questions that have already come in will be answered by either Rebecca or Ryan or someone here in the European team within the next couple of days. So to conclude then, if you would like to learn more about the environmental services from AECOM, visit aecom.com. And if you'd like to learn more about the remediation solutions provided by REGENESIS, please visit regenesis.com/EUR for the European content. Thanks again very much to Rebecca Mora and Ryan Moore, and thanks to every one of you for joining us today. Have a great day. Bye.